Meanwhile, we will be moving to the next talk from Csilla to stay on time. Unfortunately, Csilla was not able to is not able to give the talk. She had some issues, personal issues, and my understanding is that Elliot Sefton-Nash will give the talk.
Thanks very much, Sebastian. Thanks for coping with the technical challenges. So indeed, I am not Dr. Csilla Orgel, but I'm happy to give this presentation on her behalf. So landing site suitability and selections are typically based on criteria, as you know. Normally for landed missions, you would be looking at terrain properties and constraints on the operations scenario. So things like the slope of the terrain, the visibility to Earth for direct communication, and the solar illumination for photovoltaic power. And of course, as a science community, we're trying to maximize the scientific potential of any landing site. In the case for lunar South Polar landing sites, we'd be looking at, as a major factor, the possible presence of buried water ice. So this study is looking at thermal conditions that are conducive to hosting water ice in the subsurface over geologic time. And we use input from two thermal models, which are both fit to data from LRO Diviner, which is a thermal infrared radiometer. Originally, this study was driven by the Prospect payload on the Luna 27 lander, but it still holds true for the whole South Polar region for future landed missions. Another factor that is not considered directly, but is also kind of considered, is the water equivalent hydrogen abundance in the subsurface derived from LEND epithermal neutron data. So we start with the co-registered data sets for slope, earth visibility, and solar illumination, which were produced by Erwan Mazareko, and this is a well-known data set published in 2011. Of course, these data are averaged over time, so they do not consider specific time series that would be relevant for landed missions and operation scenarios for a specific mission date. We define a study area that extends from 80 degrees south to the South Pole, and this dashed white box shows that region. All the data sets are gridded to 120 meters per pixel, and regarding the thermal data, we use, as I mentioned, two models. The first is the data from Page et al., published in 2010 in Science. This model was produced at a spacing, so each node was roughly 240 meters from the next. It considers only single scattering. There's no infrared emission from the surface, and the subsurface thermal conduction is one-dimensional, so there's no lateral flow between the model nodes. The metric to calculate whether or not ice may have been stable there, whether the thermal conditions would permit it over geologic time, is used a fixed temperature threshold. For the Oxford 3D thermal model, O3DTM, published by Warren et al. In 2020, that model has a coarser spatial resolution, but it does incorporate multiple scattering, infrared emission, which is increasingly important, we now know, for permanently shadowed regions, and three-dimensional subsurface heat conduction, so model nodes can talk to each other laterally. The ice stability for that model is calculated using a theoretical sublimation curve. So the sublimation of ice in a vacuum is considered as a function of temperature. Nodes are just under 1 kilometer apart in this case, and the data extend to 76 degrees south. But in this dashed white box, both models have good coverage. So what we do is combine the places where both models show that ice could be thermally stable and produce a raster that's either 0 or 1. And it's 1 where we think ice may have been stable. All the data are again co-registered to this 120 meter per pixel grid, noting that this oversamples the model data. But we use kriging, which is a statistical estimation of the value of a field at any given point, and so we have a good handle on the variance or the uncertainty in those oversampled areas. We define 2 scenarios which broadly reflect some, let's say, end members of landed missions. One is least constrained, one is more constrained in terms of the terrain properties that any lander might be able to deal with. So, for example, in the least constrained scenario, the slopes could be up to 15 degrees, earth visibility is 25% of the time, solar illumination 15% of the time. For the most constrained scenario, for a lander that perhaps is more fussy about where it lands, the slope must be shallower, 7 degrees, earth visibility half the time, and illumination 35% of the time. Both cases, of course, require that there are locations with water ice potentially present in the subsurface according to the thermal model output. The result then is, again, a Boolean raster, 0 or 1, for each of these least or most constrained scenarios, which indicates where you might be able to target where all these factors are compliant, let's say. And you don't see much zoomed out, but if you zoom in a little, this is just the kind of central South Polar region. You can see Shackleton and just kind of lower center. There are a lot more areas, of course, in the least constrained scenario and far fewer in the most constrained scenario. And that's naturally what you might expect. But the question is, how targetable are these places? So we then use a technique using focal statistics, which is it's effectively placing a landing ellipse, a hypothetical landing ellipse, which we assume would be a circle, which is not necessarily the case for reality, but for the purpose of this study is a reasonable assumption, at the center of each pixel, and then count how many of the surrounding pixels in that ellipse are true, i.e. are compliant with the factors that we've defined. So where water ice is stable and where the terrain and visibility conditions meet those needed potentially for a lander. So what we get as an output is maps of where probability how probability varies as a function of landing ellipse placement of meeting all of your factors for a given location. So that is to say, areas with very high probability means that if you place an ellipse in those places, you get on the left-hand side, in the case of the least constrained scenario, the highest chance of success of 86% everywhere in your ellipse. So note there is nowhere with 100% success probability. For the most constrained scenario, it's much lower, of course, because there are fewer places, and so an ellipse naturally placed at those places is less likely to have the whole of its interior be compliant with these factors. Note the scales are very different on these two figures. On the left, it's 86%. On the right, it's 12%. We can also vary the size of the ellipse, and for both of these cases, we use a 5-kilometer radius. But we can explore the sensitivity of the success rate with the ellipse size. And what we find for the least and most constrained case is that for the least constrained case, we need something like an ellipse radius of about 1 kilometer, so a diameter of 2 kilometers, in order to get any ellipse anywhere in the South Polar region in our study area that has a 100% chance of success for the factors that we've defined. For the most constrained case, it's much smaller. So the ellipse radius must be much more precise, and therefore the landing system and the landing precision must be much more precise. And that's on the order of a few hundred meters. So this is the takeaway. If you want to really target somewhere that is broadly compliant with operational factors that are relevant for your spacecraft, if it's solar powered and it's a lander and it needs direct to Earth communication, and you want to target somewhere that is thought, according to thermal models, to host subsurface water ice for sampling in the present day, then these are the kinds of studies you would do to try to dimension the precision of your landing system. Thanks very much. I can take any questions, so I'll do my best to answer them on Chilla's behalf. Thanks a lot.
Great. Thank you, Elliot. Well, fantastic how you went back on time. Appreciate it. Questions from Marius in the chat regarding the focal statistics analysis. Did you consider each pixel in the circle as equally weighted, or did you apply something like a Gaussian distribution?
Hi, Marius. Yeah, that's a good question. We consider them as equally weighted. I think, the message is that you could use this ellipse as a let's just say an iso line of probability. So it's not necessarily the whole ellipse, but you could just call it, this is the entire 3 sigma. So we didn't consider any variation in the probability of pixels within the ellipse. It would add an extra dimension of realism that you would probably do for a real mission analysis. So I appreciate that. Yeah.
Then one comment I would give you, Elliot, is that the precisions that you derive at the end, how compatible is it with where the next missions are planning to go? Is this like we are order of magnitude not precise enough, or are we good?
I think it depends on the precision of the landing systems that are being considered, and of that I'm not sure. but perhaps others know better. I can say that the pilot system that would have been used on Luna 27 would certainly enable something more like the most constrained scenario, so precision of a few hundred meters to a kilometer or so.
Great, that's exactly what I was looking for. And other questions coming? In your most probable scenario, what will be the key factor compared to least probable scenario out of slopes water?
Right, so the sensitivity to the main factors. It's a good question. Well, I think actually they are all quite closely related because the topography is the driving factor. So visibility to Earth and sunlight. And sunlight governs the thermal environment of the subsurface. So I'm not sure there's any one dominant factor, and if there is, it's probably not much more dominant than the other, is my guess. Okay, hopefully that's answering your questions, Kim. Well, thanks. Yeah, it does. Excellent. Thanks, Elliot. Say hello to Csilla when she's back. We missed her, and hopefully she'll be back soon. And Csilla mentioned here on her slide she's supported by the ESA Research Fellowship Program, which I think is also the case of our next speaker.